everyone, welcome back. In the last video, we talked about the GABA-A receptors, which are ionotropic. So in this video, we will be talking about the GABA-B receptors. Remember that the GABA-B receptors are metabotropic, and they are primarily inhibitory. So they're GI receptors, right? So primarily, they will affect the excitability by coupling to GERK. We previously talked about what GERK stands for, so please go look that up if you don't remember. And GERK activation is inhibitory because it allows a calcium efflux, which hyperpolarizes the cell. So potassium leaves the cell, making the cell more negative. Okay. So the GABA-A receptor is responsible for very fast inhibitory postsynaptic potentials. However, they're also weaker. Whereas GERK is responsible for slow but strong IPSPs. Okay, so the reversal potential of the chloride ion keeps the resting membrane potential at about -70, which is that resting membrane potential. So we're not going to get an action potential, but it doesn't really change the resting potential at all. With GERK, then we're going to see that the reverse potential for potassium is actually about -90. So that is why it hyperpolarizes the cell and why it's a stronger inhibitory reaction. Okay. Talking about our agonists, then we've got baclofen. This is a specific agonist of the GABA-B receptor and is used as a muscle relaxant and antispastic. And then we've also got GHB. So this is GABA hydroxybutyric acid. This is a weak GABA-B agonist. Okay. So it is excitatory at the GABA-B receptor at lower doses. So when you use it for recreational drug use, then you can see some things such as euphoria, disinhibition, and empathogenics. However, at higher doses, it is inhibitory of the GABA-B receptor. And this is where we see GHB being named the date rape drug. So we see sedation, nausea, dizziness, and unrousable sleep, so pretty much unconsciousness. Very interesting thing is that GHB was designed by researchers. It was made in a lab because they wanted to find a blood-brain barrier permeable prodrug analog of GABA. But it turns out that GHB is actually an endogenously produced neurotransmitter. So your body does produce GHB by itself. It's a naturally producing neurotransmitter, but in very small doses. We don't make a lot of it. And the GABA-B receptor is this endogenous receptor. Okay, but because our body naturally only produces a little bit, this is what we get. We get excitatory reactions of the GABA-B receptor with endogenous GHB. We know this. We know that it's widely expressed. So GHB is not just in one part of the brain, but like all over the brain. But we don't study it. We don't really know why it's there. We don't know what its original use in the brain system is, but we just know it is there. We do know that the GHB receptors are excitatory, and they tend to increase glutamatergic activity in specific regions. And you can actually use GHB in specific doses to treat narcolepsy and other sleep disorders. So using small doses of GHB, we can treat narcolepsy, treat sleep disorders, which is very interesting given that at high doses, it causes sedation and sleep. So Well, most GABAB receptors are GI coupled receptors. It's possible that the GABAB receptors that GHB is binding to is actually a GQ coupled protein. And it acts on IP3 levels. That's really all that we kind of know about it. People just tend not to do a lot of research on it. Okay. So I mentioned the most popular, the main way, probably like over 90% of these GABAB receptors are GI, and they work on GERK, G protein coupled inward rectifying calcium or potassium channels. So that's what it is. So here we've got our G protein coupled receptor. Okay, so this would be our GABAB receptor. Okay. GERK opens on a binding of the G beta gamma. Okay, so that's this. This is otherwise a regulatory component of the G protein complex. So you see it's there. It'll remove itself and then go and act on GERK itself. And this is what then causes that potassium to leave the cell, which leads to that hyperpolarization. Okay? GERK signaling will then inhibit subsequent depolarizing stimuli. So because we are hyperpolarizing the cell, it's decreasing the probability of other receptors opening, allowing ions into the cell that would then depolarize. Okay? Because we're hyperpolarizing the cell membrane, we would need even more positive ions into the cell to depolarize it, but we're preventing that with this hyperpolarization. Okay. Oh, it is Rho. I knew it. Okay, GABA A Rho receptors. So we're back to the GABA A receptors for a bit. Just because I mentioned that these are very unique, and so I didn't want to throw them in with the other receptors. The GABA A Rho receptors is very unique. It's a GABA A receptor where we only have the Rho subunits. It used to be called a GABA C receptor, but then it's ionotropic, so they're like, well, I guess it's technically a GABA A and all that. But what's interesting about it is it's insensitive to both baclofen and bacuculin. Okay, and that's because it doesn't have binding sites for benzodiazepines, barbiturates, and neurosteroids. Because remember, we talked about how those binding sites have to be between an alpha and beta. And since these only have Rho subunits, that's not possible. Now, it is very sensitive to GABA, though, because it has 5 GABA binding sites. GABA can bind in between every single subunit. So, if you only have GABA someplace, then your ideal receptor would be this GABA A Rho, because then you only need GABA and you'll get activation all the time. We tend to find these receptors in the bipolar cells of the retina, and this would then receive those inhibitory signals from the amacrine and horizontal cells. Okay, because remember, we get GABA, and GABA itself is inhibitory, so we're receiving an inhibitory signal. Any mutation to this GABA A Rho receptor is going to be associated with different disorders in the retina then, especially heritable cases of retinitis pigmentosa. So, if we look at the retina, these are the cells within your retina, the different types of cells you see here. We've got our ganglion cells, amacrine cells. There's those bipolar cells. We've got horizontal cells, and then our rods and cones. So retinal transmission is largely dependent on various inhibitory steps. Okay, so you can see here we've got inhibitory neurons that are GABAergic, whereas the other cells would not be GABAergic. They'd probably be glutamatergic, okay? So rods and cones themselves have tonic excitatory cells, and then they'll be inhibited by light, okay? So rods and cones are kind of just always active, but when you hit them with light, then that's when it leads to inhibition, and that's what tells the cells, like, oh, hey, I saw something, okay? Amacrine and horizontal cells provide modulatory input to the bipolar cells and are responsible for modulating that visual field and moderating sensitization, including balancing those inputs from the rods and cones, which is really important when we have low light. That's also why we don't get as much information when there's low light, because then we don't get that inhibition of these rods and cones, all of that fun stuff. So our GABA A alpha rho receptors are on these bipolar cells. They are getting information from those horizontal cells, also from the amacrine cells. You can see here they're also getting information from the cones and rods. All very exciting. Okay. Now, what is the role of GABA in development? I kind of mentioned this a little bit in Monday's lectures, but GABA plays a large role in development, especially because as we get older, we develop more inhibitory systems, which is what leads to what we call maturation, okay? So here, GABA development in the prefrontal cortex is a late developmental step, okay, associated with maturation of impulse control, working memory, and executive function. So we get those fine motor movements because of this increased inhibition. So what this is showing is this top line here is showing the amount of excitatory synapses that we have in our prefrontal cortex, and then down here, this line is showing us the amount of inhibitory synapses in that prefrontal cortex. And this on the x-axis is age, y-axis is percent, so 100% excitatory, 0% excitatory, that would be what we see. Here we see from fertilization to birth of different things. So there's proliferation, migration, different things that's going on within the neurons. But if we just look at the types of synapses we have, you see that when you're born, almost the majority of your synapses are going to be excitatory. And we actually peak at around age 5. That's your age when you're going to have the most excitatory synapses you'll ever have throughout your entire life. From there, we start to prune them down. And then during puberty, so around age 15 to your late teens, is when you're going to kind of even out to the amount of excitatory synapses you'll have. So when you're about, say, 18 to 20, you're going to plateau at about 40% excitatory synapses that you'll have for your life, okay? So that's not saying only 40% of the synapses in your brain are excitatory. I'm saying out of all the excitatory synapses possible, you're sitting at 40% possible, okay? If we look at inhibitory synapses, you start out very low, almost none until puberty, okay? Then in puberty, that's when you start to increase the number of inhibitory synapses that you'll have throughout your life. And those they start to plateau in your early 20s, but they really keep increasing until about 25. Okay. So this is that you're getting mature, you're becoming an adult phase, might be making some bad decisions, but still, having fun, you're figuring things out. And then you start to kind of some people might say you get boring as you grow old, but that's because you have your inhibitory things. You've figured things out. Your impulse control is under control, I guess. I don't know. You have great working memory. Your executive functions are great. And so you can see here kind of that after age about 18, your inhibitory synapses are going to take over from those excitatory synapses. So what can this do to our behavior? Well, it can obviously then change the effects that GABA has on our behavior. So anxiety is associated with GABA a bit, not as much, of course, as it is associated with serotonin and norepinephrine, but it is still associated. So generalized anxiety disorder or social anxiety disorders, panic disorder, PTSD, etc. These are all types of anxiety disorders. And what we see is that we can treat them with some GABA agonists and some positive allosteric modulators, so such as benzos and barbiturates. They do have some anxiolytic effects, not as good, definitely worse safety margins than our SSRIs and SNRIs, but they're still pretty good. There's a few models of suggesting how that's working. So one saying that anxiety is caused by the secretion of endogenous inverse agonists of the GABA receptors. And this would then inhibit the GABA receptors, which would then increase anxiety perhaps. And that's why these positive allosteric modulators would be anxiolytic, because it would reverse that inhibition. And then we've got ligand activity at the GABA receptors is shifted in anxiety, so perhaps there's different subunits. Maybe instead of that alpha, alpha, beta, beta, gamma, we have more alpha, beta, deltas or something. I don't know. That's a suggestion, because that would then also change the binding sites that are available. And then the third possible model would be secretions of some sort of endogenous agonist of that benzodiazepine site during stressful conditions. So is there this endogenous agonist of that benzo site? If there is there less secretion of this endogenous agonist during anxiety? Is that's what's happening? Or, some people have also suggested maybe there's an endogenous antagonist of the benzo site, and that increases during anxiety. We don't know, because GABA is not one of those receptors that's studied extensively in anxiety. People tend to study serotonin, norepinephrine, dopamine, those ones when talking about anxiety rather than GABA, because GABA tends to be more upstream from the specific place of anxiety and depression. In development, I mentioned the role of GABA with that inhibition, and high levels of GABA and developmental changes in GABA activity leads to that excitatory inhibitory switch. So again, we're not turning off all the excitatory, we're just decreasing the amount of excitatory and increasing that inhibitory. GABA may also contribute to cell proliferation, survival, and motility. So maybe we need the GABA for that to continue to occur when we're adults, because when we're younger, we have all of these cells when we're born, and we actually have too many, and we have to prune them all. Well, after a certain point, we now have to start making new cells. We can't just continue pruning. So perhaps GABA is playing a role in that as well. This excitatory inhibitory balance is very important for maintaining normal brain development. And we've actually, this balance, this EI balance, has been associated with a number of conditions, such as Down syndrome and autism spectrum disorder. has been suggested that it's an EI imbalance that's leading to some of the symptoms of these disorders. Okay. GABA, again, I did mention this a bit before, does play a role in epilepsy because GABA is the opposite of glutamate, and we know glutamate can be a convulsant, then GABA can be an anticonvulsant. So again, it's this excitatory-inhibitory balance that's implicated in the seizure disorders, having an imbalance between glutamate and GABA. So any drug that decreases GABA or inhibits GABA receptor functions are known as convulsants. They can lead to seizures, epileptic seizures or non-epileptic seizures, and any drugs that increase GABA levels or increase the function of those receptors can be anticonvulsants. This EI imbalance in Down syndrome and autism then correlates with the increased risk of seizure disorders as well. So that's another reason why this EI imbalance is implicated in a number of disorders where you see a large comorbidity with epilepsy or other seizure disorders. So, finally, we've got psychiatric disorders that can be affected by GABA. GABA is implicated in a number of different psychiatric and neurodegenerative disorders. We've covered a couple, but there is developmental disorders like ASD. We got addiction, learning disorders, schizophrenia, Huntington's, Parkinson's, all of those. GABA is implicated. A lot of times it's because GABA is so prolific, and it is, even if some other neurotransmitter is implicated, so say in Parkinson's, then dopamine is highly implicated. Well, what's upstream from dopamine? GABA. So perhaps it's not just the dopamine, but perhaps it's something upstream, such as GABA is malfunctioning, leading to that malfunction of dopamine or something like that. So generally, GABA is proposed to contribute to hyperactivity through decreased inhibitory signaling as well. So ADHD and such would be implicated with GABA. Perhaps patients with ADD, ADHD, other hyperactivity disorders, or inattention disorders just lack this inhibitory control. They weren't able to develop that EI balance that is needed for what we call normal function. Okay, so that is it for GABA. You will notice in your slides there is a summary here of glutamate and GABA. I'm not going to go over it. You guys can look through it. It's just a nice summary. Yes, you need to know it. If there's a table, I would at least look at that table and know most of it. But that is it for GABA.